Hello everyone, this video explains the different resistive phenomena in semiconductors. Most importantly, it talks about a newly theorized phenomenon named induced change in resistance. Let us see what this is all about. We begin with static resistance, which is the most common form of resistance in semiconductors or otherwise. Then we talk about dynamic resistance, then conductivity modulation, and finally induced change in resistance. We will also see how the last three categories are related to each other. Let us get in. As we can see here, whether it is p-type or n-type, where a voltage is applied across them, the current that we obtain is a linear current, which means that when the voltage changes by say a factor of alpha, the current automatically changes by the same factor alpha so that the resistance remains constant. So this is called static resistance. However, something very different happens when this p-type and n-type are joined together to form a p-n junction. Now, when a forward bias voltage is applied across them, we can see that this gives rise to a non-linear current, unlike the previous case. This non-linear current gives rise to different slopes at different points on the current line, and these different slopes, as we know, gives different resistances. We call this as dynamic resistance and define it as dV by di. We can also define a large signal resistance, which is just V by I, large signal dynamic resistance here, given by V by I. And here, similarly, we can see that if we try to change the voltage by alpha, the current now changes by beta instead of alpha, and this change actually gives a change in RD. It is no more remains constant now because alpha and beta are not equal to each other. So we get a dynamic resistance. If we try to give a reason here why this dynamic resistance has now come in, unlike the previous case, here you see when the majority carriers move across the junction, commute across the junction to a region where they are called minority carriers, then this in fact gives rise to a non-uniform distribution of charges, unlike the previous case where in the case of conduction current where there was a uniform distribution of charges. Here we get a non-uniform distribution of charges. As we can see here that when say the holes from p-type move to n-type, the number of holes are much higher in the p-type because they are the majority there, and in n-type they are much lower because they are in minority. So there is certainly a concentration gradient from left to right. That means there is a higher concentration at left and lower concentration at right, and this creates a diffusion current on top of the conduction current which already exists. This diffusion current actually changes the charge density at a given location with the change in the voltage, and which is why we also see a non-linear current and a dynamic resistance. Let us look at this at a greater detail. Here we have considered an n-type semiconductor before the formation of the junction and after the formation of the junction. As we see here that in this type, as we have already talked about, that the charges are uniformly distributed. So and the current is a conduction current, mostly conduction current. So here, say if we take a cross section A, and let us say that this cross section has 3 electrons, then when the current flows, these 3 electrons will be replaced by another 3 electrons, and these current 3 electrons will exit to the right. So from the left there will be 3 electrons coming in, and from here there will be three electrons going out of the same cross section A, and the density of charges will be maintained constant in case of conduction current. Unlike the case when the junction is formed, here we have a good presence of diffusion current over the conduction current, and that means, as we can see here, since the holes have migrated from the p type to n type and the current is from left to right, as we can see that left has a greater number of charges and the right has a lower number of charges. So when the current flows at cross section A, a higher number of charges at the same cross section replaces the lower number of charges already present, and those lower number of charges will move further right. Now, as a result, what happens is, as per this famous equation, as we can see here, that if we change the density of charges, and certainly we do that because here, since higher number of charges are now coming into A and replacing the lower number of charges, that means the charge density has now increased. So a change in the charge density will change the conductivity of it, that is sigma, and that will in turn change the resistivity. Here mu is the mobility, and the resistivity will change the resistance as well. Therefore, a change in the voltage, in this case of diffusion current, the change in the voltage will create a change in charge density at a given location A, and that will change the conductivity, and that will in turn change the resistivity as well as resistance. So this phenomenon is called voltage driven conductivity modulation. We can call it resistivity modulation as well, and also resistance modulation. Now we come to the most important part of this discussion, that is induced change in resistance. It is really now simple to understand what this is all about. As we have already seen that a change in voltage in case of diffusion current changes the resistance at, say, cross section A. Now the same diffusion current, when it goes across to B, then it changes the resistance of that location as well. Therefore, here what we can say is that due to the change in resistance at point A, there is an induced change in resistance at point B due to the diffusion current flowing from A to B. Here we must remember that point B is connected, electrically connected to point A, and this is simply called induced change in resistance. Though this is simple to understand, this has brought a great change in the way we see the current mechanism of the diode, current and voltage mechanism of the diode. Here, the PN junction diode to be particular. So the current, now with this kind of phenomena defined, the current can be more accurately modeled to match the measured results. So this has been reported in one of my papers published in the IEEE transactions on CAD of integrated circuits and systems, where I have shown that my diode equation, which is the modified diode equation, is much accurate as compared to the existing Shockley's equation, and my equation has an excellent agreement with the measured result, unlike the Shockley's equation. We can know more about it from the following references. So in the fourth reference, as you can see, this is the paper I was talking about. Here I talk about the induced change in resistance for the first time, and however, this particular phenomenon is discussed in greater detail in another paper that is a preprint available freely on the IEEE Tech Archive, some analytical perspectives of nonlinear circuits. Thanks for watching. Please share this video as much as possible for the benefit of the scientific community. Thank you.